Hello and welcome to this session, Learning Outcome LO1. Understand enthalpy changes associated with exothermic and endothermic reactions. Today we will learn, how does heat energy change during chemical reactions? This video explores the concept of enthalpy changes in chemistry and explains the differences between exothermic and endothermic reactions. Enthalpy is the total heat energy of a system. In chemical reactions, we focus on how this energy changes. The change is called enthalpy change, represented as delta H. It indicates whether heat is released or absorbed. This is crucial for understanding reaction dynamics. Exothermic reactions release heat to the surroundings. Energy released is greater than energy absorbed. As a result, the surroundings warm up. The enthalpy change is negative, meaning delta H is less than 0. Products have lower enthalpy than reactants. Energy is needed to break bonds in reactants. However, forming new bonds in products releases more energy. The excess energy exits the system as heat. Combustion, neutralization, and respiration are examples. These reactions are essential in daily life. Endothermic reactions absorb heat from surroundings. Energy absorbed is greater than energy released. Consequently, the surroundings cool down. The enthalpy change is positive, so delta H is greater than 0. Products have higher enthalpy than reactants. Breaking bonds in reactants requires more energy than forming new ones. The system absorbs extra energy from surroundings. Thermal decomposition and photosynthesis are examples. These reactions are vital for processes like plant growth. Understanding them aids in energy management. Enthalpy profile diagrams visualize energy changes. The vertical axis represents enthalpy. The horizontal axis shows the progress of reaction. Exothermic reactions slope downwards, while endothermic reactions slope upwards. The vertical difference between reactants and products represents delta H. Activation energy is the minimum energy needed to start a reaction. It represents energy needed to break bonds in reactants. On diagrams, it is the energy difference between reactants and the highest point of the curve. No reaction occurs without sufficient activation energy. It is always positive. In exothermic reactions, products have lower enthalpy than reactants. The diagram slopes downwards overall. Delta H is negative, indicating energy release. Energy released during bond formation exceeds energy absorbed. EA is measured from reactant energy level up to the peak. In endothermic reactions, products have higher enthalpy than reactants. The diagram slopes upwards overall. Delta H is positive, indicating energy absorption. More energy is absorbed breaking bonds than released forming new ones. EA is still measured from reactants up to the peak. Standard conditions allow fair comparison of enthalpy values. Temperature is 298 Kelvin. Pressure is 100 kilopascals. Solutions have a concentration of 1 mole per cubic decimeter. Substances are in their standard states. These conditions ensure consistency in measurements. This is the enthalpy change when 1 mole of a substance is completely burned in oxygen. It occurs under standard conditions. The process is always exothermic. The value of standard enthalpy of combustion is always negative. This demonstrates the energy released during combustion. This is the enthalpy change when 1 mole of a compound is formed from its elements. It occurs under standard conditions. Only 1 mole of product is formed. Elements must be in their most stable forms. The standard enthalpy of formation of an element in its standard state is 0. This is the enthalpy change when a reaction occurs in stoichiometric amounts. It happens under standard conditions. The change can be exothermic or endothermic. It depends on the balanced chemical equation. This highlights the importance of stoichiometry in reactions. Enthalpy changes can be calculated using average bond enthalpy values or experimental data. Average bond enthalpy is the energy required to break 1 mole of a particular bond. Experimental data involves temperature change calculations. Both methods have their own merits. Understanding them aids in accurate energy assessments. Average bond enthalpy values help calculate delta H. Breaking bonds absorbs energy. Forming bonds releases energy. The formula involves subtracting the sum of bond enthalpies of bonds formed from those broken. Results are approximate due to average values. Accurate bond counting is crucial. This method uses temperature change data to calculate energy transferred. The formula involves mass, specific heat capacity, and temperature change. Energy transferred is converted to kilojoules. The value is then used to calculate delta H per mole. This practical method provides realistic results. Hess's law states that the total enthalpy change is the same regardless of the reaction route. It depends only on the initial and final states. Enthalpy cycles show alternative pathways between reactants and products. They are used when delta H cannot be measured directly. This principle is based on energy conservation. These cycles use standard enthalpy of formation values. The key rule involves subtracting the sum of standard enthalpy of formation of reactants from products. This method is useful for calculating unknown enthalpy changes. It provides a systematic approach to energy assessment. Balancing equations is essential. These cycles use standard enthalpy of combustion values. All substances are combusted to the same products, usually carbon dioxide and water. The key rule involves subtracting the sum of standard enthalpy of combustion of products from reactants. This approach is crucial for combustion reactions. It highlights the role of energy release. In conclusion, this video provided a comprehensive overview of these principles, highlighting their importance and practical applications. If you have any questions, please feel free to contact us via WhatsApp at 0748 436 1688. We look forward to seeing you at the next session. Thank you for your attention.